Hi everyone, my name is Shaik Khaleel. I'm an assistant professor, Department of Data Science. Today in the lecture of data structures, we are discussing the topic graphs. Now here introduction to graph. Graph is a non-linear data structure which consisting a set of nodes as well as vertices. Graphs are so many types we can see. We have directed graph, undirected graph, weighted graph, unweighted graph. So these graphs may be seen in number of combinations: weighted, directed graph, weighted, undirected graph. In graphs, we are having nodes. This can be called as an node. Total in this graph, how many nodes we are having? A, B, C, D, E, F, G. All these are nodes. Each and every node in a graph is connected with the help of an edge. This can be called as an edge, and this can be called as an vertices. Graph G is a collection of node as well as vertices. The graph may be, this graph can be defined as undirected graph. This graph can be defined as directed graph. We have a particular direction from A to B or from A to D. Either it may be A to C, like B to D, E to F, D to E. These are all directions. This graph doesn't have any sort of directions. If you are trying to represent weights, weight means a node that carrying some value that could be called as a weight. For example, this A to C we're having weight, so called 7. C to G we're having weight, so called 6. Like this kinds of graph can be called as a weighted graph. Here in graph, any node to be connected with any other node with the help of an edge. Just like as a tree, graph is also a nonlinear data structure. So these are the terminologies that we have to remember while discussing about these graphs. A graph is, we know that graph is a consisting of nodes, can also be called as vertices, and that nodes are connected with another node with the help of an edge. So vertex is the fundamental unit of a graph which can be represent an entity. So like this A, B, C, T, that might be of anything that defines something about this particular graph. Edge is used to connect adjacent vertices, the two vertices which are adjacent to each other. Degree of vertices means the total number of edges incident to that particular vertices. Suppose if you want to find the degree of this A, how many edges are incoming as well as outgoing. If it is an undirected graph, we can able to say the degree of a graph particular vertices node A is 2. If you want to find this degree of the node B, that node, the degree is 3. But because from D we are having a node, D we are having an edge to B, from A we are having an edge to B, and from C we are having an edge to C. Like this 3, like this 2, like this 2. These all are represent the degree of the particular vertices for this directed graph. Some more important terms we have to represent path. A path defines that particular way from source to destination. For example, if we consider from path A to B, B to D, D to E. Now here the length defines 3. Here we are having an example of a path and cycle that encloses in between of all these vertices. A to B, B to D, and D to E. It is a path. Path defines a particular way from source to destination. The length of the path defines the total number of edges we are trying to connect. First, second, third. Like this A to B1, B to D2, and D to E3. This defines the length of the particular path. Now cycle defines the closed path between all the vertices which are going to be connected with the help of edges, and that can be called the cycle. Connected graph, a graph where which there is a path between every pair of vertices. For example, like this, see, this is a connected graph. There is no such vertices that we can't say it is connected. Now if it is a disconnected graph, we can say these are two parts of a graph. It's like subgraph. Not each and every vertices are not connected. These are disconnected graph, but though even we can able to consider it as a graph. This is an example of connected graph, and this is an example of disconnected graph. So here self loop defines we have a path that can traverse the same vertices, and this could be called as self loop. Whereas B and C cannot be called as self loop. Parallel edges, we are having multiple edges between of two nodes. For example, consider there's a two edges lies between of B to C and C to A, and that can be defined as a parallel graph. Now what do we can say it as in a complete graph? See, every pair of vertices is connected. If you see selected this graph, B is connected to every vertices. B is connected to A, B is connected to C, B is connected to D, B is connected to C. Like this, every vertices if you select, to that of each and every remaining vertices is going to be selected, and those kinds of graph can be defined as complete graph. Now here this weighted graph as well as acyclic graph. Acyclic graph means there is no particular formation of cycles, no closed path. Weighted graph, previously we have we would have some weights according to their edges. Acyclic graph represents that there is no cycle formation. Here if there is an edge slice between D to A, then this could be called a cyclic graph. As of now, here no edge lies between of D to A, hence it is an acyclic graph. See, here we have whatever the data that we are trying to represent in terms of graph, and those are represented in two ways, primarily in two ways. The first thing, list representation of a graph, and that could be called as an adjacency list. And the second thing, matrix representation of a graph, that can be called as adjacency matrix. Here the list we have a same like as a linked list. We can call it as a linked list. A node is connected to another node which holds the address. Based on the address, a node is connected to another node. Here also in the same fashion, a node which is a neighboring node to that of neighboring node to that of, so how many nodes are connected with this particular vertices? All these nodes are going to be connected with each other. Like these kinds of representation can be called as linked representation. Can also be called as that can be used with the help of an adjacency list. For example, consider a graph consisting of 5 vertices A, B, C, D and E. So this graph is going to be represented in the form of adjacency list. So first we have to define this node A. We have to ensure this node A connected with how many other nodes, like B and C, direct connections. Like B if you consider connected to A and D, like C if you consider connected to A and E, like D if you consider connected to B and E, like E if you consider connected to D as well as C. Like these kinds of representations can be called as adjacency list representation. If there is an edge lies, if there is a weighted lies in between of A to C, for example 2, again we have to give some space, 2 we have right here. For example, A to B 3 and A to C 2, like this here 3 we have right, here 2 we have right. There is no further more connections, then simply we can able to represent as null, empty. For no weights, we are going to take a single node. If there is a weight, we have to take the node of double representation. That's all about adjacency list representation of a graph. Now we are going to see about adjacency matrix. How this matrix is going to be represented. See here, for example, take all this vertices of 5, same graph we are going to consider here also. One matrix we have to draw number of rows as well as number of columns with the help of this vertices names. If there is a self loop lies, if there is a path, that could be represented with 1. If there is no path, that could be represented with 0. Assume that A to A there is a path, no path. That's why we are representing with the help of a 0. A to B we are having a path, so we can represent 1. A to C we are having a path, 1. A to D, do we have a path? No. That's why we are representing with 0. From A to E, again 0. Again, now we have to consider from B. B to A we have a path, yes, 1. From B to B, no self loop, 0. From B to C, no loop, no path, that's why 0. From B to D, yes, there is a path, 1. From B to E, no. Like this consider from C, like this consider from D, like this consider from E. If there is a path lies between of two edges, and that could be represented with 1. If there is a no path, that could be represented with 0. Like these kinds of graphs can be, graph representation can be defined as adjacency matrix representation of a graph. So one more graph terminology we have to remember is an isomorphic graph. So isomorphic graph do have these 3 rules very importantly. If we are going to say the graph is an isomorphic, the graph contains same number of vertices and the graph contains same number of edges. The degree remains same. For example, see here graph G contains V1, V2, V3, V4, V5. Total how many number of vertices are there? 1, 2, 3, 4 and 5. Now see how many number of edges are there? 1, 2, 3, 4, 5. The first point matches. Total number of, same number of vertices, same number of edges. Now just you need to calculate each and every vertices do possess the same number of degree or not. So vertices 1 if you consider, see vertices 1 getting an edge from vertices 2 as well as getting an edge from vertices 5. Thus degree represent to be 2. Now vertices 4 2. Getting an edge from vertices 3 and getting an edge from vertices 5. If we consider vertices number 3, getting an edge from vertex number 4 as well as getting an edge from vertex number 2. So here also 2, here also 2. If you consider the three things similar, and the graph can be considered as an isomorphic graph. Here also same thing. How many edges we can able to see? 1, 2, 3, 4, 5. See, vertices 1 having how many number of vertices? Degree 2. Here also having degree 2. Here also having degree 2. Here also having degree 2. Degree 2. Degree can be defined as total number of incoming edges as well as total number of outcoming edges. As previously we have discussed, each and every edges aligned with the total number of vertices. Edges, vertices, degree. These both are same. Edges, vertices, as well as degree. If these three remain same, then that could be called as an isomorphic graph. There is no fixed shape that we can able to define it as an isomorphic graph. The shape may be vary. So graph G also, graph G1 also, these both are isomorphic graphs just because of following these three rules. Degree, vertices, edges of a particular graph should be same. Structure may not be the same. So the powerful nonlinear data structure is a graph. As previously we discussed, in this real world, if you want to connect this graph system, so we can able to use this graphs in social networks, connecting of each other in transporting system like Google Maps. If you consider all this particular every from source to destination, eventually we found this shortest path based on this availability of the route. In a networking system, each and every computers are connected with the help of this graph technology. So how do we search data? Through the help of web linkages. One web page to another web page is directed with the help of a graph. Each and every packets of the data helpful to receive the data based on the availability of the data packets. That's all about graph data structure we have discussed. Thank you.